Welcome, John. Very good to see you. And it only occurred to me when I was confirming our arrangement for tonight that we've had a lot of your colleagues from the University of Glasgow join us on these meetings. I think we're up to about 30 now, and I think 4 or 5 of the speakers have been from Glasgow University. So thank you and your institutions for supporting this group.
I wonder if you must have had Graham Wone speaking at some point.
I think so, yes. I was going to check the names, and I just didn't. I just didn't get a chance before this meeting because we've been travelling and I've been kind of distracted a little bit. But I'm always encouraged when professional academics give up their time to address us, and I've never been refused, and I just want to say thank you, John. It's a real privilege to have you with us tonight. Many of us do astronomical and geophysical measurements in sheds at home, and we build stuff and write code and play. But I've got a feeling that we're not going to be able to build anything to measure gravitational waves. So that'd be extremely interesting. So without any more waffling on from me, just one more thing. Is Callum on the call tonight? Are you there, Callum? Oh no, did I see you?
Yes, sir.
Perfect. Callum's got something to share with us a little bit later. And being on a minute screen, I just couldn't confirm that Callum was with us. Okay, John, you should be able to share your screen. Thanks again, and over to you.
Okay, let me just make sure that we've got the right setup here.
Looking good.
So this is giving me reminders of the last couple of years of teaching on Zoom, which was never the most fun experience, but in this case, it's a good way to reach a broader audience. So hopefully now you can see some slides, or you
Indeed.
can see a slide. Can you give me a thumbs up just to check?
Yes, you're looking good. It looks like you're in presentation mode.
That's good. Okay.
Listening to the universe, it says.
Let me stop this again because I'm sharing the wrong screen. That's the problem. Let's see.
And you spent 2 years working on Zoom.
Yep.
I love it when the Radio 4 presenters say, "You're still mute, you're still mute."
How's that?
Yep, looking good.
So can you see the single slide?
A single slide, listening to the universe with gravitational waves.
All right. Well, then here we go. Well, first of all, thank you very much for inviting me to give you a talk. As I was saying, I spoke to my colleague, Graham Wone, who's a radio astronomer by background, and he was like, oh, there's some very good people in that group, and it made me think, maybe I need to treat this a little bit differently from your average public outreach talk. So, well, you can judge for yourselves how well the concepts come across, but I've tried to put in a little bit more technical details than I would normally to an average amateur astronomy group. And I'm very happy to talk if there's questions at the end or if anything's not clear. You can keep a note of any questions and we'll come back to them at the end. I'll just try and run through things as best I can, and we'll come back at the end. So first of all, I'll introduce myself. We've got a nice photo of myself here at the LIGO Livingston Observatory, which is not your traditional observatory. And I will be telling you all about what LIGO is, including where Livingston is. It's not Livingston in Scotland, unfortunately. That would be a lot more convenient for me. But I'm a senior lecturer at University of Glasgow, and I work most of the time on gravitational waves, particularly with these LIGO detectors and looking at black holes and neutron stars. And my speciality is in the number crunching So if you're talking about people writing code and tinkering their sheds, I totally sympathize with that. I think if nobody was paying me to do this, I would probably be doing something anyway. Yeah, I hope to encourage you to keep going. And you say that you've been having difficulties detecting gravitational waves in your shed. But from what I hear from Graham, there are people actually doing kind of pulsar timing even with amateur equipment. So as you'll see later on, it's maybe not as far removed from the realms of possibility as you might think. So what I'm going to talk to you about is these 4 topics. What are gravitational waves? How do we detect them? Because that in itself is a very exciting challenge. Where do they come from? How are they produced? And what can they tell us about the universe? And there's too much to go into the full detail on all of these topics, of course. So I'll just try and give you the kind of first or second level overview as best I can. So the first question is, what are gravitational waves? And in order to explain that, I have to say, well, what is gravity? And in particular, we can take our minds back right to the dawn of modern science with a chap you may have heard of called Sir Isaac Newton. And he was the first one to recognize that gravity was a force that didn't just apply to things falling down on the earth, but actually held together any masses anywhere in the universe. And if his famous equation F equals gmm over r squared, that every student will learn in school, hopefully, is the Newtonian gravitational force. So that's what keeps the planets moving around the sun, and what keeps apples falling onto Sir Isaac's head as he's sitting in the garden back on Earth. And when he discovered this law, and he realized that with this he could predict the elliptical orbits of the planets, and he was able to actually go a bit further than that, not just the shape, but he could show that the period of the orbit of the planet should be proportional to the radius, or the semi-major axis, really, to the 3/2 power, which is, of course, Kepler's third law. And so he was very chuffed with himself, as you would expect. And there's a quote that he gave is, "I've explained the phenomena of the heavens and of our sea by the force of gravity, but I have not yet assigned a cause to gravity." So he himself knew that the theory, though it could make very good predictions about how the universe looks, it doesn't actually tell you why gravity is a thing. It just says, here's the law. There's no mechanism to actually explain how it works. And so this remained a bit of a mystery for a few hundred years as the rest of modern physics developed. And it took a long time for people to reach the point where this technical detail of how do you actually explain what gravity is, it's not just this forced law, what's going on under the hood. And it wasn't until the late 19th century that things really came to a crux. So the first pointer towards something being wrong with this law of gravity, well, there was a emerging evidence from the perihelion advance of Mercury, but really on a theoretical level, what put the kibosh on Newtonian gravity was what's called the Michelson-Morley experiment. So there's a reason I'm introducing this now. And if you've ever studied physics at university, you probably will be aware of this experiment. So this chap, Michelson here, and his colleague Morley, set out to measure the speed of the Earth through the luminiferous ether, as it was called at the time. So this was based on the idea that light was a wave, and waves are always found traveling through a medium. So if there's a medium that transmits light as a wave, then the Earth must be able to move with respect to that medium. And so you should be able to measure the absolute speed of the Earth against that medium by measuring the speed of light in different directions. So they built this apparatus, which is now called the Michelson interferometer, which was designed to measure the speed of light as you rotate it in different directions. So the idea was that at the vernal equinox, the Earth would be moving in one direction. And so you would measure the speed of light in the X, Y, and Z, well, only in the X and Y directions because it's on the table, and then wait for the autumnal equinox, and you would get the opposite velocity as the Earth travels around the sun. But to their surprise, they could never, ever detect any actual change in the speed of light relative to this apparatus in the laboratory. So this was the first real verification that the speed of light is the same in all reference frames. So how can that be? Well, this is the challenge that was set to the theoreticians around about the end of the 19th century. So because this Michelson interferometer, we're going to encounter it again. I want to actually show you a modern day version of this. Now, Michelson didn't have a laser, of course, back at the end of the 19th century, and he had to use white light from a white light source in order to do this, which is amazingly much more challenging than it is with a pure light source like a laser that you can highly collimate it. It has a monochromatic wave, but nonetheless, the experiment worked. But these days we would use a laser, and what will happen is that the light will come from the laser. I don't know if I can have a pointer on this, actually. Maybe that would be useful. Well, the light comes out the laser, it hits that beam splitter in the middle of the picture, and half of the field continues straight on to hit that test mass on the right, and the other half of the field gets split down to the test mass on the bottom. And these are two mirrors which reflect the light wave, and it comes back up and recombines at the output. So it's got this very kind of characteristic cross shape. And when we take this apparatus out to science fairs, etc., then we're able to do this. And it's very sensitive at measuring changes in the length of the arms or changes in the velocity, if you like, because you can take the first derivative of that. And people have great fun banging on the table, and we hook up some microphone so they can hear tiny vibrations and so on. So this is the basic idea that we'll come back to when we start talking about LIGO. But before we go there, we were coming at it from a bit of a theoretical angle, and in order to explain how the speed of light can be the same in all reference frames, we really have to take a hammer to Newtonian dynamics, and that's what happened next. So I'm going to try and explain to you in a couple of slides what the key difference is between physics as Newton did it and physics as Einstein will do it. So in Newtonian mechanics, the world was very simple. Isaac Newton said there was a single reference time everywhere in the universe, and all clocks will beat at the 1 second per second, no matter where they are, no matter how fast they're moving. And you can draw a line everywhere, or rather you can slice the entire universe into a future and the past, just by taking the t=0 slice through everywhere at every point in space, if you like. So in this Newtonian diagram, we can put space on the x-axis and time on the y-axis, and then a speed, if you like, will be given by distance over a time. So that will be represented by a line with a certain gradient, and the shallower the gradient, and this the way I've drawn it here, the faster something is moving, the more space it will cover in less time. Okay. So that's the Newtonian picture. That's what everybody learns at school, and it makes a lot of sense because if you're using, Cartesian coordinates and so on, this is all built up to solve this type of problem for hundreds of years. It all meshes together very nicely, but it doesn't explain how light can be the same in all reference frames, because in this picture, if you measure the gradient of that line, you should always find that it has the same. Or rather, you should find that you'd be measuring it relative to the gradient of your own line. So if Isaac Newton is in the center here, moving straight up from the past to the future, he would measure a certain gradient. Somebody who was moving themselves, if they went to measure the gradient of that line, they would measure the gradient relative to their own line. So, okay, that's easier to explain when you have a pen and paper, but hopefully you get what I'm saying. But this was overthrown in 1905 when Einstein decided that the special relativity theory was what was needed to explain this constancy of the speed of light. And the real conceptual difference to this is that the notions of past and future no longer apply everywhere in the same way that they do in Newtonian dynamics. And really what's happened is that the present, rather than being a single slice, is now kind of a wedge. There are lots of positions at certain times that you can say are simultaneous. And the idea of what is simultaneous now depends on whether you are moving or not. So this is the relativity of simultaneity. And basically everything, all the consequences of special relativity can be derived from that one concept and from this one diagram, if you like. But I can't show you on this diagram, but now if you're moving around in this picture, you'll find that the speed of light is kind of set by this boundary between the past and the present, or the present and the future. And it represents a maximum possible speed that anybody can travel at. So this idea of there being a kind of wedge between the past and the future is taken up in the 20th century by theoreticians, and it gives rise to one of the really nice ways of explaining how general relativity will work. So if we take that wedge, let's just make it 45 degrees to make things a bit easier. We can say that now, if we look at the slice of the future and the slice of the past, we've got what's called a light cone, which is kind of a cone shape in this two-dimensional projection that I've drawn, where the speed of light sets the angle of the cone. And anywhere inside that cone, if you were a red particle moving on that red line, that would be a perfectly valid world line, as it's called. So if you're a material object, you can move anywhere inside your light cone, but you cannot move outside your light cone. So this explains why you can never reach the speed of light, why you can never go faster than the speed of light. And it breaks the whole universe into a sort of nested series of light cones. And you can actually derive a lot of the consequences of general relativity just from that picture. So we're going to go there now. It's like, what's this got to do with gravity? Well, remember that Isaac Newton said gravity is an instantaneous force acting at a distance. Einstein says nothing can travel faster than light. So they're going to have a face-off here, and no prizes for guessing who it is that's going to come out on top. So really making this Newtonian idea of gravity agree with the theory of special relativity was Einstein's big challenge after he'd come up with special relativity. I mean, the guy has some ambition. You've got to give that to him. He said, well, I'm going to overthrow Newton a second time. So it took him 10 years, but after thinking for 10 years hard, he came up with the general theory of relativity, and that's his theory of gravity. So that really describes gravity not as this action at a distance, not as this force law that Newton had, but it does give you some kind of mechanism for how gravity really works. And the simple way of looking at that is in this slightly low resolution diagram. These light cones that I've introduced a few slides ago, you can put a light cone at every point in space-time, and the influence of gravity is really to just jiggle the way that they're pointing a little bit. So remember that because any material object has to move inside its light cone, if that light cone is tipped over a little bit, as they are here towards the right, then it's going to naturally move in that direction, even though it thinks it's at rest. Because of the structure of space-time, it's actually going to get pulled over towards a gravitating mass. And if you think about gravity in that way, it actually gives you a nice way of viewing a black hole, which is also shown on this slide. Because what happens when those light cones get tipped over by 45 degrees? It means that it's no longer possible for anybody to move towards the left. So that point, that line here on the space-time diagram, where the cones get tipped over by 45 degrees, marks what's called the event horizon. And that's the surface around the black hole. It's not the real surface, it's just a surface of demarcation between the places where you can escape, where you can move to the left, and the places where you cannot escape, where you have to move to the right, in towards the center of the hole. And once you're in the middle, you'll encounter the singularity and be crushed, of course. This also gives you a nice way of viewing why that has to happen, because the singularity is not really a point in space now, if you think about it. If you're on one of those world lines, you're going to hit the singularity at a point in your future. So it's like trying to avoid, 9 p.m. There's just no way to escape. Time forces you into the center, no matter what you do to try and escape. So this is the pictorial view, and this is one of the ways to understand it, and it's one of the ways to kind of grasp what general relativity is saying. When I teach this to my students, of course, I have to use the equations just to make it hard for them. And the equivalent of Newton's F equals gmm over r squared is this g mu nu equals 8 pi g over c to the 4 t mu nu. And really what it's saying is that there's I've actually got this the wrong way around. That's embarrassing. So the red label should be pointing to the t, and the curvature should be pointing to the g. I must remember to fix that. But it's really just saying that mass is causing space-time to curve, and by curving we mean that these light cones are tipping around. So that's one of the consequences of the curvature. So rather than having a mysterious force, we actually have this idea that gravity is a stretching of space, is just an effect of geometry, in other words. And a mass will cause stretching of space, and then when an object tries to move in a straight line, as Newton's law says it should, it cannot, because you cannot move in a straight line in a curved space, basically. So that's the consequence. And the picture that you've probably seen is this kind of rubber sheet view of the universe to get across the idea of curvature. And then an orbit of a planet around the sun would become an ellipse, where it's following, trying to follow a straight line, but actually being curved by the surface. Although this is really an analogy, it's a weaker analogy than the idea of the light cone. So I'd like to try and move away from it. Okay, so this is the modern view of gravity. We still don't know what space-time is made of. That's really one of the outstanding questions. And even Einstein realized that he didn't explain that. Whether there was some kind of atoms of space-time is another question. But that's still an open question to this day. But one consequence of this theory is that gravity doesn't travel faster than light anymore. It means that there has to be a time delay between something happening and the gravitational field updating itself everywhere in the universe, and that the speed that the influence will propagate is actually the speed of light, as we will see later on. So you have no longer got instantaneous action at a distance, but that speed's traveling at the speed of light can carry that influence traveling at the speed of light can actually carry energy away. And just the same way that a light wave is change in the electromagnetic field, you can have a change in the gravitational field that will be a gravitational wave. Okay. So here is a picture of a gravitational wave. An animation on the top shows you the effect as it moves through a cylinder. And you can see what's happening is it's sort of stretching, it's moving towards the left here. And as it moves, it's stretching space in one direction and then squashing it in the opposite direction, and then vice versa. So it tends to transform a circle into an ellipse. And the way that you can see this is also in this sort of effect on a ring of test particles in the bottom half of the slide, where it's moving in these two different patterns. Just as light has horizontal and vertical polarization, gravity has two polarizations as well, but rather than being horizontal and vertical, they're actually called the plus and the cross. So the reason for that is because if you imagine taking the left polarization there and rotating it through 90 degrees, then you're actually just going to get back the same effect that you had in the first place. So the polarization states are not separated by 90 degrees. With gravity, they're separated by 45 degrees. And there's a nice technical reason for that we can get into later if anyone's interested. But this is the change in the geometry. If we want to quantify that, we put a number attached to that called strain, which is anybody who's ever done mechanical engineering will be able to tell you is the change in the length divided by the length. So it's just like the strain in a material and a block of elastic. You can measure that by the fractional change in its width. This is exactly the same mathematics that's used to describe this effect in general relativity. So whenever you see H or hear me talking about strain, I'm talking about a fractional change in the length. Okay, so that's the one picture of gravitational waves. I said that they're a bit like light waves. Well, let's see how far we can take that analogy. So if I take this slide that was kindly provided by Graham, so you may have seen it before. He gave me the dipole antenna patterns for a dipole antenna. So hopefully this is something that everybody's familiar with. If you want to detect a radio wave, you want to create an antenna that responds optimally to one of these polarization states. And the way to do that is to take the split wire, so the voltage across it is maximized, and the optimal length for each of them is lambda by 4, and we can take 2 of them to get the best combination. So you know more about this than I do because I'm not a radio expert, but the picture certainly makes sense to me. And a dipole antenna is not equally sensitive in all directions because it has this antenna response function. So gravitational wave detector, if we know how to detect radio waves, we want to do the same kind of thing for gravity waves. So remember, one of these polarizations in light, it's a linear polarization, or in radio, it's a linear polarization. But for gravitational waves, we have this cross-shaped polarization. So our antenna, rather than being a straight line, a dipole, it has to be a quadrupole, which is the shape that gives you this right angle measurement that will optimize the effect of the strain on the detector. So if you remember the Michelson-Marley experiment from earlier on, what we actually have is one of these Michelson interferometers. So we'll come back and talk about them in a second. I wanted to point out that because the effect of a gravitational wave is the change in the length, we have actually a big advantage if we make these detectors as long as possible. So we have made ones that were initially a few meters in the lab, then up to 50 meters, and then up to 600 meters. And now the ones that we're using to make astronomical observations are 4 kilometers long. And their antenna response function, just like in a dipole antenna, they're not equally sensitive in all directions, but they are, they respond to the 2 different polarizations in these different patterns. So you can see that they're not directional things. They're not like a dish, and they're not like a telescope that you point. They're much more like a microphone, like a dipole. So you're really listening, and the analogy is with sound rather than with light in that respect. And the analogy is actually a very close one for LIGO because the frequency that it's sensitive to is pretty much the range of human hearing. So between about 20 hertz and a few kilohertz in the case of LIGO. Okay, so let's go back to these Michelson interferometers. So I'll show you a diagram or a movie again. This is what happens when the gravitational wave comes along. So this interference pattern that's produced by the beam splitter is going to change because you can see that as the light beam moves up and down the arm, the phase of the wave will be determined by the length of the arm, the number of cycles that fit into that 4 kilometers. And if the 2 arms are exactly the same length, then the phase will cancel out when they recombine with the beam splitter. And it's only when they begin to change in length through the influence of the gravitational wave that you will have a change in the output. And you can pick that up with a photodetector just as you would for any other laser. And it's that change in the length, a change in the light power on what's called the output port, is what we actually measure. Okay. So let's put that all together, and we've got our Michelson interferometer here. The gravitational wave is moving, changing the length of the arm. You can see that the interference pattern is changing and producing a change in the light power on the output. Now, that's how you detect them. I haven't said very much yet about how they are produced. So I'll take a brief moment to give you some idea of why we need to have arms that are 4 kilometers long. So just as you can have a dipole electromagnetic emitter, you cannot have a dipole gravitational wave emitter, unfortunately. The reason for that is that momentum is conserved, which is an interesting theoretical underpinning of this. So you have to look to the quadrupole, not only for detection, but also for emission. And so you end up with what's called the quadrupole formula. The equation on the top right, if anyone's got a maths background, you can see it's related to the third derivative of the moment of inertia of the source. But what's particularly important is that it's this constant at the front is g over c to the 5. So g is Newton's constant, is 6.67 times 10 to the minus 11. C is the speed of light, which is 3 times 10 to the 8. So that number at the front is extremely small. 10 to the minus 11 divided by 10 to the 40. So it's like 10 to the minus 51 or something. Nonetheless, because the moment of inertia for the sources that, well, another way of putting it is that in order to get an appreciable luminosity, we need a very large moment of inertia. So moment of inertia is given by mr squared, basically. So you want a very large mass at a very large radius, but because we're taking the time derivative of that, what we really want is something that's orbiting very fast, so that the moment of inertia is rotating. So really what we're talking about is binary stars. So one of these things, each binary star, if it's got a mass roughly equal to the sun, that's 2 times 10 to the 30 kilograms. And then the radius can be a few thousand kilometers in the case of the black holes that we'll be seeing later on. And it's really because that they're orbiting so fast that you get a huge power from the source. And actually, if you plug in the numbers, it's enormous. You get the luminosity in gravitational waves is on the order of 10 to the 46 watts. For this audience, I decided I would convert that into a spectral flux density for the wave at the Earth. So even though it's hundreds of megaparsecs away, because the luminosity is so high, the spectral flux density for one of these sources is actually around about 10 to the 20 Janskis. So you can compare that with your radio astronomy observations. So you think that would be trivial to see that kind of thing. But unfortunately, it's not, because it turns out that the amount of energy it takes to stretch space is absolutely enormous. So the coupling constant is really very poor. So it takes, this number of watts of power to stretch space at the source. And by the time that gets to us, the effect on the strain is about 10 to the minus 22. So a fractional change in the length of the distance between here and Alpha Centauri of roughly 1 width of a human hair or something like that. So it's an effect that is really, Einstein thought that these would never be detected because he knew that these numbers were way too small. And it was kind of an impossible dream for a long time to even try and attempt to do it. But the dream, it turned out, was actually founded on some good science. And through enormous amounts of ingenuity, we were able to build what are now called the LIGO detectors. So I'll show you pictures of these. First of all, we've got LIGO in Livingston, in Louisiana. That's the one where my photo was taken. It's in a kind of swamp in the middle of kind of the backwoods country in the deep south. It's quite an interesting place to visit. You can see the big arms, 4 kilometers long. You've got what's called the X and the Y arm, as it doesn't take much imagination to see why. And then the edge of those arms, because we're in a swamp, there's got to be a trench full of water just to catch the runoff. And so if you ever visit this site, you can see the sort of alligators swimming up and down the arm length. It looks pretty close to an evil villain's hideout as you would ever see in real life. With the possible exception of LIGO in Hanford, which is the other detector in Washington State in America. Hanford, if you've not heard of it, is the place where the plutonium was made for the atomic bombs that were dropped in the Second World War. The Hanford site, as it's called. It's pretty much the most radioactive place in the Western Hemisphere. Blasted desert where there's not much around except for nuclear weapons reactors. The first time I went to visit Hanford, actually, I left the town of Hanford, which is just to the south, and drove north and realized that the place that I was going, the roads just stopped and the map was completely blank. It's because the site had not been declassified by the time that map was produced. So it was quite difficult to locate LIGO back in the early noughties. So yeah, it's another very interesting place to visit, but not where you'd want to spend a huge amount of time, I suspect, especially if you weren't wearing a lead-lined underpants. If you were a tourist, then you would definitely want to go and visit the Virgo detector, which is the other large-scale ground-based detector, because that's just outside of Pisa in Italy. The climate's lovely, there's farms around, the food is amazing, and there's all the wine you can drink. So if you've got to go and do an observing shift, you probably want to pick this detector, even though its arms are only 3 kilometers long. So those are the 3 big ones. There's also GEO 600. In Germany. It's only got 600-meter arms, so it's not used very much these days for astronomical observations. It's never really been able to detect anything because it's not powerful enough, but it was an excellent test bed for a lot of the technologies that we'll be seeing in a minute. And I should also give a shout out to Kagra, which is a Japanese detector that they're currently commissioning. That's in the Kamioke mine in the same place as Super K neutrino detector. And that should be competitive in a few years' time, but they're still, well, they're planning on booting it up for the first real observing run in the next few months, but we've yet to see how it's going to perform compared to LIGO. So I thought I would give you a little rundown of the insides of these things, because as I say, it was an impossible dream, but there was a work of hundreds of people to make this dream a reality. And it turns out that basically every component that goes into these detectors had to be invented for the purpose of detecting gravitational waves. So first of all, on the outside, you see these arms. Now, obviously, you don't want to shine your laser beam that's very sensitive to vibrations through the air, because you're going to get very poor seeing, even in the best possible conditions. The motion of the atoms of gas in the air will perturb the laser beam. So the whole thing is placed inside the world's largest vacuum system. It took a long time to evacuate the beam pipes. You can see the scale of them here with some of the technicians in their clean room suits. So the whole chamber was evacuated. It's got a larger volume than the vacuum tube at CERN, which I think is the second largest. And in order to make sure it was a pure enough vacuum, once you pumped all the air out, they had to pass a huge electric current through the metal arms, through the metal beam pipe, to force any remaining gas atoms that were trapped in the lattice of the metal out into the pipe through heating. And then they were pumped away. So this costs a huge amount of money in electrical power, as you would imagine. But it was back in the 90s, so wasn't so much of a concern back then. Each of the arms contains a huge vacuum system, and they're linked together at the vertex, as it's called. So this is the world famous origin of the Euclidean axis, carefully kept by scientists at Hanford. So the 2 arms here, the X arm is the one on the left, and the Y arm is the one coming down towards the bottom. And the beam splitter and the meat is in that vacuum tank in the center, with the technician standing on a ladder just in front of it. And you can also see the port where the laser beam is coming in, just on the right-hand side there. So it gives you an idea from the tabletop experiment that Michelson and Morley performed, how much things have had to be scaled up for this level of sensitivity. So what about the mirrors inside the interferometer? Well, we've got instead of just the white light reflectors, we've got ultra high finesse optical cavities inside each of the arms. So the light is actually bouncing around inside the arm hundreds or even thousands of times to form a laser cavity. And it's through that repeated bouncing up and down that it picks up the phase change due to the length changing from the gravitational wave. And each of those mirrors is suspended from a single piece of glass, which is built by what's called silica welding. So this is basically like having a wine glass where the resonant frequency is extremely pure. It means that through the thermal vibrations that you cannot get rid of, if something's at a finite temperature, its atoms are going to vibrate. But if you make the resonant mode very, very pure, then all the vibrations of the heat will tend to be dumped into one particular frequency. And then you can just damp that frequency away, and the rest of the frequencies will be left relatively quiet. So this is the trick that was used. These are extremely, I think they're the highest Q pendulums in the world. You can see here that they're dangling from multiple stages. Each time you add another stage to the pendulum, it kills off any ground motion by a factor of 1 over frequency squared, or F over F naught, where F naught is the resonant frequency of the pendulum. So by hanging multiple pendulums from each other, you get a factor of 1 over F to the 8 for a quadruple pendulum system. So this is actually really powerful. If the resonant frequency of this pendulum is 1 hertz, and we're making measurements at 10 hertz, then we're suppressing the noise that's being transmitted through the system by a factor of 10 to the 4, basically. Sorry, 10 to the 8. So that's a really good passive isolation system. On top of that, we have active isolation that tries to cancel out the ground motion. So that whole pendulum is suspended. It's down below this apparatus here. This is a special table that's built on servos that damp out any ground motion that can be picked up in the lab. So you can see the lengths that people have gone to isolate this object from its environment. And then, of course, there's the laser itself. There's a close-up of one of the mirrors there. These are actually one of the largest objects I think that have ever been put into a quantum mechanical state, because it's such a pure environment that the quantum mechanical effect of the laser beam is transmitted onto the mirror in isolation from the environment. The laser itself is ultra stabilized, as you would expect. So you don't want any frequency noise ruining the experiment. So there's a very complicated process of cleaning light. You know, it's extremely pure. You only want a single frequency. You only want a single mode of the laser. So there's a very complicated optical layout of the input laser. And you can see that that was all basically invented for the purposes of LIGO. The input laser in advanced LIGO is between 50 and 80 watts at the moment. So this is only a small part of the overall apparatus. And then the whole thing is controlled from the control room, which looks like the kind of mission control system at Houston. And it has a great number of sensors. There's over 100,000 environmental channels in the LIGO system as a whole that can be used to clean data and so on. And the whole thing is controlled using supercomputers, and that's also what we use to process the data. Okay, so it's hopefully giving you the impression it's incredibly high tech. It just happens to be located in the absolute backwoods parts of the United States. So here's Hanford in tumbleweed season. They tend to blow through the desert, and because there's a giant 4-kilometer arm in the way, they get piled up against the side of the detector. So every now and again, somebody has to go out with a pitchfork and clear away all these tumbleweeds from the side of the detector. And if you're not being plagued by the local flora, then it's probably the fauna that will get you. In this case, the police force in Hanford like to drive around the desert in the middle of the night, as it turns out, without realizing that they could collide with this gigantic beam tube and come out the worse. So yeah, we've got a few local difficulties at both sites between that and the alligators. Okay, so I'm just going to wrap up. I'll tell you, here's now the slightly more complicated picture of this Michelson interferometer. Inside the arms, there's 100 kilowatts of light power bouncing in the cavity. So that's, again, to suppress the statistical effect of individual photons hitting off the mirror. You want to reduce that by throwing a hell of a lot of photons at the mirror. So you definitely don't want to be in there without your protective glasses on. And once all of this has been assembled, we get down to a sensitivity of strain sensitivity. If we convert it back to strain on something about 10 to the minus 23. So 1 part in, as I say, the distance between here and Alpha Centauri to a human hair or thereabouts. So it is achievable. Took them a very long time to make it happen. But nonetheless, this is now up and running and making detections. So I could say more about the details here, but I think in the interest of time, I'll skip on. One fun thing is that this is now sensitive enough to measure the gravitational field of a graduate student standing up and sitting down. Okay, so here's the obligatory logos, selection of the universities and research institutes that were involved in building these detectors and operating them as well. And you might see a few local institutes up here for yourself. All right, so I think I've said enough about detection. I'm kind of running out of time, in fact, so let's move quick to sources. So just as there's an electromagnetic spectrum, there's an entire spectrum of gravitational waves, ranging from the extremely long wavelength waves that were produced in the Big Bang and then redshifted way down to low frequencies, up through things coming from supermassive black holes up to stellar mass black holes and neutron stars and supernovae. And it's really the stellar mass end of things that LIGO is designed to detect. So we'll be focusing on LIGO, and there's these 4 main classes of sources. We can roughly divide them into whether we know what they look like and whether they're short or long. So we have modeled and transient, unmodeled and transient for supernova, modeled and continuous for pulsars, and then unmodeled and continuous for the stochastic background. That's like the primordial background of gravitational waves. And the only one we've detected up till now is these compact binaries. So I'm going to focus on these just now. These are these in-spiral binaries. So for LIGO, what's crucial is this compactness, because it's the size of the object that determines how rapidly they can rotate around each other, because otherwise they would just crash into each other. So a white dwarf is what's usually called a compact star, and everybody knows that a teaspoonful of white dwarf matter will weigh a few billion tons in the surface gravity of a black hole, of a white dwarf. But they're not compact enough for LIGO because they're just too big. And it's really neutron stars and black holes, which are roughly 10 kilometers in diameter or radius, are the type of things that we're looking at. And their masses are between about 1 solar mass and, well, we'll see is several hundred solar masses, perhaps. So black holes really are a very interesting phenomenon. It's one of the reasons that I got involved in this, because I was wanting to find out more about them. You'll see this kind of funnel diagram of the warped space-time. I can show you the more scientifically accurate version of this. This is the result of a supercomputer simulation of one of those black hole binaries merging. So you can see those gravitational potentials coming together as the stars are orbiting, and they're giving off radiation, so they're getting closer together as the orbit decays. Once they're within a certain point, a common event horizon will form around both of the black holes, and that final black hole will just settle down into a nice stationary state. And if we zoom out, we'll see all the gravitational waves propagating away at the speed of light from the merger. And that's exactly what LIGO detected back in 2015. So hopefully you will hear the sound when I play it now. So I don't know whether the sound came through okay, but if you heard that, then you'll have heard the low frequency thud, which is the actual frequency of the wave. It's around about 240 hertz. And then the thing was frequency doubled to make it a little bit easier to hear. looking in detail, this waveform, you can divide it into the in spiral, where the two things are orbiting around each other, a merger and a ring down. And each of these bits of the signal is a really nice way of looking at the physics of what's going on in these extreme gravitational field scenarios. This regime has never been probed before. Even the pulsar timing measurements can't get to this level of curvature. So this is the best place we have at the moment for testing the theory of gravity. Just one more movie for now, showing you the effect of the gravitational lensing of the holes as they are orbiting around each other at the end. And you can see that actually it's not as violent a process as you would expect. It's kind of stately. Of course, this is slowed down by a factor of a few hundred. But you can see the space-time really warping in this process. And then the final horizon forming just there and settling down. Yeah, so it's actually, if you were about 1,000 kilometers away from this, you would be able to feel it, but it wouldn't hurt you. So the coupling between the gravitational field and the energy is really what's saving us there. Sorry, it's playing backwards for some reason. Okay, so as I was saying, the huge amount of energy that's dumped into the space-time, the peak luminosity of this merger was about 10 to the 49 watts. In other words, it was the equivalent of converting two solar masses times the speed of light squared through E equals mc squared every second into pure energy in the gravitational field. And by looking at the shape of the waves, we can tell quite a lot about what the source was, and we know that the black holes that formed this were about 35 and 30 solar masses, roughly speaking. So they're pretty big. Before we observed this, nobody actually knew whether this type of black hole existed out there. So it was a surprise in many ways when we first turned this instrument on and saw this signal. The wave also tells us quite a lot about the spin of the black holes. I don't think I've got time to go into the details here, but that's an astrophysically interesting topic that we could come back to later if we wanted to. That final black hole, just to put it to scale, is roughly speaking the size of Scotland. Yeah, it's got a total mass of 62 solar masses, having lost about 5 solar masses in the process of merging. It's 20 million times the mass of the Earth. The system's rotating about 100 times a second. And you definitely wouldn't be anywhere near to it because you'd be spaghettified by an enormous G-force of about 20 billion times the surface gravity of the Earth. Okay, I'm just going to skip over this because I don't have got time to go into the details just now. Although one thing I did want to point out is this jet. So we did not see a jet in the scenario that we were talking about just now because there was no matter in the system. It's just two black holes coming together. But at the moment, we're going to look at another type of system which does have jets. So after operating LIGO for the last 7 years or so, we've accumulated quite a lot of these black hole mergers. And you can see that the masses range between a couple of solar masses all the way up to over 100. So it turns out there's a huge range of types of black hole out there. And we presume they're all formed through the process of stellar evolution. And the next challenge is really to understand what those processes are doing to make these very massive stars. That's something that's not really well understood at the moment. So before we wrap up, I can't let you go without saying a few words about multi-messenger astronomy, because obviously you guys are radio enthusiasts. And you almost certainly will have heard about GW 170817, which was not the merger of a binary black hole, but was the merger of two neutron stars together. So this is the case now where we do have matter in the system. The signal, to put it in context with the binary black hole signals, here's some binary black holes at the top, binary neutron stars on the bottom. And if you listen carefully, there should be an audio playing of the waveform from this one. So we'll let it play out for a second, well, a few seconds here while I talk. But the point I'm really getting to is that the number of cycles that are contained in this signal is several thousand compared to a few dozen in most of the black hole signals. So from all those thousands of cycles, we're able to pick up a huge amount of extra information that we can't get from black holes. And that's because the stars are orbiting more slowly, being lighter mass objects. So I'll just stop talking for a second and let you listen carefully, because you can just about hear the merging of the binary neutron stars. There you go. As again, it's a very surprisingly artificial sound for something that's a natural phenomenon. It sounds like a kid's toy or something, you know. It's always fun to play that to a classroom full of kids. So the information we get about the neutron stars is a lot more detailed. You can see the measurement of the mass is really accurate in this one particular chirp mass direction. And it's really that tells us that they have to be neutron stars, because we don't think there are any black holes that have masses this low. And they certainly can't be white dwarfs, because they wouldn't be able to inspiral to these frequencies. So I've got another simulation movie to show you. This one's for the binary neutron star merger, and in particular, I want you to watch carefully what's happening to the stars as they're approaching the end of their inspiral. So they're starting to elongate because they're feeling the effect of each other's tide. So just like there's tides on the surface of the Earth, there's actually tides raised on these neutron stars by the companion's gravitational field. And that stretches out the star. So it's just like a rubber ball where you can squash it in one direction and it will respond. And then once they've merged, they will form a hypermassive neutron star, possibly for a few seconds. And then there's too much mass to support, so that will collapse into a black hole, form an accretion disk, and therefore launch a jet. So this is very exciting for us because, well, A, we can get some information about the neutron star by measuring the effect of these tides. It turns out that that effect is imprinted onto the gravitational wave signal. So one of the things that we were able to do with this system is try and measure the squishiness of neutron stars, which is something that has not been done before. And I can't really think of many other ways to do it outside of, well, NITER and also a few nuclear physics experiments that can hope to address this question. From the enormously longer signal, which reaches higher frequencies, we also can localize the source a lot better. So here's a map of the Earth, well, a view from the North Pole, showing you the location of the main detectors. And you can see that there's a sort of long baseline between the American detectors and the European detectors. And that's important, of course, because we're interested in localizing the source in the sky. So if you've ever studied diffraction, you will know that if you can measure the phase at 2 points, then there are only certain combinations where certain directions where the waves can possibly have come from, represented by the places where the waves constructively interfere. So in this case, that's given by this formula here. The opening angle is given by lambda over 2d. It gives you sine of theta over 2. And in case of the two LIGO detectors, if you work out what that is, should be around about, between the LIGO and Virgo detector, the light travel time there is 27 milliseconds. If we assume a frequency of around about 150 hertz, which is the optimal sensitivity for the detectors, we should be able to localize things to a few tens of degrees in the sky. I think I'm just the effect of a greater baseline on the system. So there we go. There's the 27 milliseconds between Virgo and Hanford. And that's what allowed us to actually localize the source of this gravitational wave quite well. Now, this is purely from the gravitational wave observatories, this sky map here. But it actually happened that at the time the signal was detected, there was a gamma ray burst observed by the Fermi instrument and also by Integral. And that was also able to be localized to an overlapping patch in the sky with a larger diameter. So this launched a worldwide scramble as people started pointing telescopes to try and see if they could find the source of the gravitational waves and the gamma ray burst. So lo and behold, after a few hours, the SWOPE telescope and DLT spotted the electromagnetic counterpart indicated with the crosshairs here, just outside of the host galaxy. A better image is given here. NGC 4993, that number will be ingrained in my memory for the rest of my life, I think, as being a very exciting counterpart. And of course, this was a view in optical. As time wore on, the detritus from this collision started to cool down. And it was observed first in the gamma rays by Fermi, but also in X-rays, in UV, optical, infrared, and radio. And it's still being observed in the radio as the jet from the GRB propagates out. Okay. So I'll give you a slight sample of the things that we can do with this, other than the interesting fact that we now know what produces gamma ray bursts and therefore lots of exotic elements. By identifying the host galaxy, we can measure the redshift, and it turns out that gravitational waves will give you a direct measurement of luminosity distance. So this gives you a completely novel way of measuring the Hubble constant. So within a few days, people had already done this analysis at a crude level to work out what H0 is, which is currently a matter of quite heated debate between early universe and late universe measurements. So there's a lot of interest in finding another way of trying to decide the battle. As you can see, the gravitational wave detection doesn't give you a very good constraint. That's the blue curve, is basically the probability that the Hubble constant is anywhere between about 50 and 140 kilometers per second per megaparsec. But in the future, as we get more and more signals, we'll be able to pin this down a lot more. So I wanted to just finish up for you guys digging into this a little bit more. It turns out that that measurement of luminosity distance is highly correlated with the inclination angle of the source. So that's given the symbol iota in this graph here. So we can plot now the two-dimensional result for the inclination angle and the Hubble constant. You can see that there's a large range, a large correlation between those two things. So if we had another way of measuring what the inclination angle is, then we would end up with a better constraint on the Hubble constant. And so it's really that's coming back to the radio. With the VLBI, people have been able to measure the superluminal motion of the jet and therefore work out what the inclination angle is for that jet. And if we assume further that the jet is launched in the direction perpendicular to the orbit of the gravitational wave, then we will see that we can narrow that down a lot more and therefore get a better measurement of the Hubble constant through better distance measurement as well. Okay, so I'm going to wrap up there just to look to the future for a minute or two. LIGO will be back online in the next couple of months for the 4th observing run, which will be hectic for me. Looking even further ahead, there'll be the 3rd generation detectors, which will be powerful enough to see almost all of these black hole mergers throughout the whole universe, all the way back down to the era of reionization. If we go to space, we can make the detectors much bigger and see much bigger black holes. That's what LISA's for, and that will launch in the 2030s. And then if we go to the very longest wavelengths, pulsar timing arrays are also pretty close to making a detection, I think, of the stochastic background from cosmological and supermassive black hole sources throughout the universe. So the things are heating up all across the gravitational wave spectrum at the moment. If you're one of those shed tinkerers who wants to get their hands dirty, I would highly encourage you to go and have a look at the Gravitational Wave Open Science Center, where you can download all of our data, which is now public, along with a lot of the data products from these analyses. Some of them are things that I made, so you have a personal connection there. I'm happy to help explain them to you if you ever run into difficulties. Just drop me an email. Okay, so that's the end of the talk. I'll leave you with this inspiring look back at the whole gravitational wave spectrum and open the floor in case you have any questions. Thank you.
Thank you very much, John. I noticed we've already have a question in the chat from Peter. Just trying to get it there. Can you see that, John, on your screen?
I think I have to stop sharing for a second to do that. Or rather, I have to stop. Here we go. Okay.
Yeah, Peter Lloyd was talking about Weber's observations in 1987.
Oh yeah, Weber. So the Weber bar, I'm not sure it was from 87A. I think it might have been earlier. There were several claims of detections. Maybe I'm thinking of a different one. Yeah, so the idea of these interferometers, I can actually just pull the slide up again for a sec. If I go back, this was not the initial design for the interferometers. They started off with blocks of aluminium, and they thought, well, in order to detect gravitational wave, we want a really big mass, obviously. So they took a large block of aluminium, and as the gravitational waves came through, it would resonate on the mass. The sensitivity of those instruments was really not very high, and I don't think they would have been able to detect supernova 87A, as far as I'm aware. Otherwise, we would have seen other things by now with LIGO that we haven't seen. So at least the community was very paranoid when I was a graduate student about making false detection claims for this reason, because it's so difficult to verify these transient things anyway. You really need multiple detectors. That's why there's 2 LIGO detectors. But that bar, it got split in 2, and a laser got put in between the 2 halves of the bar, because then the distance between the 2 halves of the bar would change. And then they realized, well, actually, I can just make the 2 halves of the bar very far apart, shine a laser beam in between them, and that led to the idea of this resonant cavity. And then the next stage after that was, well, why don't we put another resonant cavity at right angles to get the perpendicular effect, and use a single laser so that the frequency noise cancels out. And really, the LIGO, it wasn't a leap, it didn't come out of the blue. It actually came from the evolution of these bars. And there's even one of these split bars in the basement of the Kelvin building in Glasgow, where I work. It's quite interesting to go and have a look at it. I don't know if that answers the question. Why didn't LIGO use Weber's techniques? Well, it turns out that the Weber bar is really not that sensitive. There are actually other bar detectors. They're very good at a single resonant frequency of the apparatus, but even there, they're not as good as LIGO, unfortunately. Shall I read on to the next one?
Yes, please. Yes,
from Richard
as well. Yes.
So there's a few years ago, a Dutch team reviewing the first set of results from LIGO criticized the LIGO administrators for lack of access to data and the measurement models used. I don't know exactly of the team that you're thinking about. There was the Danish Niels Bohr Institute, I think, were the first ones that came along. There was a lot of clamor at the time for the data. I don't think the LIGO response was quite as you say there. The people were nervous, I would say, because again, the worries about false claims, but there's all these hundreds of thousands of environmental channels and so on that need to be isolated, and then there's glitches in the data as well that could be mistaken for false alarms. So the analysis has to be done pretty carefully. Nowadays, there are lots of people independent of LIGO who do that, and indeed some of the LIGO groups have even left the collaboration for various reasons. But I think things have settled down on that side, and the data is fully open now anyway. A third vertical arm to a space detector. Yes, this is one thing I would like to do, is have a 4-kilometer tower also, because that would give you it would give you a measurement of the other polarization state in every case, which would be nice. But it'd be probably quite impractical to do that. You could maybe imagine drilling 4 kilometers down into the earth, but again, the benefits versus the cost is probably not that great. But yeah, it is a good idea in principle. The cylinder detector was earlier, and yeah, I think that's right. It was at 60s and 70s. Then there were others that came along later as well. And Jim Huff was the guy at Glasgow that was working on this for decades, and Ron Drever, who went over to Caltech to start up the LIGO lab there with Kip Thorne and Barry Barish. And Ray Weiss, of course. Sorry, Ray Weiss. Does the sensitivity of the instrument scale linearly with the length of the arms? Yes, it does. So that's really what you're measuring is the change in the length. And so the change in the length is equal to the length times the strain. So if the strain is a constant, then you increase the length and make the change in the length bigger. Okay, I think that's all the ones in the text. Why the pipe such a large radius? Yeah, that's a good question. So one thing that I didn't really get into is on the mirrors, you see they're about the size of somebody's head here. That's because their surface is vibrating from heat. So obviously those vibrations are much bigger than the size of the effect that we're interested in. So we have to average the length over a large area. And that is, the laser beam is therefore actually about a foot across. Actually, it's not quite a foot across in LIGO, but it will be that size in future detectors to sample the surface. And then the beam tube has to be bigger than that. You could make it smaller. The vacuum tube itself is not as big as the beam pipe that I showed you in the desert, but it is, a couple of meters across. I'm not sure if there's an overwhelming reason why it has to be that size. There must be a good reason, but I'm not aware of it. I know that there's problems with scattered light that can happen just from like any residual particles of dust, or even little shiny speckles from the laser beam. I think you probably get away from that if you can install baffles. So there are baffles around the mirror inside the beam tube to try and block any stray light.
Martin, can you unmute and ask your question real time?
Yeah, I hope so. Thanks very much. Can I say thanks? That was a great talk. I really enjoyed that. I learned a lot about it. But I was going to ask you something a bit more about a practical sort of problem. I noticed all three of the sensor, or all three of the instruments, are actually fairly close to seismologically active zones. You've got the Washington's north of the San Andreas Fault and the Pacific North American plate. The Louisiana is not far from the Caribbean and South North American plate. And of course, Pisa is a well-known earthquake area. I was wondering, do you have a problem with detecting or inadvertently detecting earthquakes and particularly S waves, I would imagine, shaky waves, rather with these instruments? And how would you get around them?
Yeah, that's a very good question. That they do detect earthquakes. It's actually the problem. It doesn't actually matter where they are in that regard, because we basically see every significant earthquake in the world vibrating the instruments. So we have to get rid of them. We just throw away the data. And in fact, any nearby earthquake will knock the instrument out of lock and overwhelm the control system. So they do come down quite a lot just from environmental effects. What's more important is the type of earth that they're built on and how easily it transmits the vibration and whether it resonates. It's not, so we can damp out a lot of the seismic motion with the controls, with the isolation systems. What we cannot damp out is the effect of what's called Newtonian noise, Newtonian gravity gradient noise. So if you imagine a pressure wave actually for an earthquake moving through the earth, obviously it's a pressure wave, it's longitudinal, and it compresses the rock as it's moving. And when the rock's compressed, it has a greater density than when it's decompressed, right? And because it's got a greater density, the gravitational field from that part of the rock is greater than it is from the the out of cycle part of the rock, where the rock is decompressed. And so even with perfect seismic isolation, we would still detect the force of gravity pulling us towards the peaks of the seismic wave, which you cannot screen out because it's gravity that you want to detect in the first place. So yeah, so earthquakes are a big problem, but maybe not in the way you were thinking.
A great functionality test then, in some respects, I suppose. Anyway, thanks for that. I thought I couldn't see how you could get around it. I guess you just have to null it out in some way. But I do appreciate the hardness of the ground around you and its ability to absorb, particularly I was thinking of S waves might be the problem, actually, because they have they move traversely across the Earth, and they also have a pressure component as well. But I was thinking more from the actual compression of the instrument rather than the effect of gravity changes. But anyway, thanks for that.
We're pretty good at keeping the instrument as it should be. If something comes along that's really that big, like a powerful earthquake, it will just completely knock it out of control.
Yeah.
We have to just, take it offline and start again. And that happens roughly once a day.
Oh, good, eh? All right. Well, thanks very much anyway. It's a superb talk.
Well, somebody's asking about odd vibrations. There's a good one. So they wanted to build, they are actually building a detector in India. And one of the things that the environmental monitors measure is, of course, the seismic waves that we're just talking about, because you need to be able to check what the environment is doing. And we had trouble getting this data out of India because they were concerned that it would reveal the presence of nuclear weapons testing. And it was a matter of national security that they would not release their seismic data from LIGO India when it was being commissioned. It's not actually up and running yet, but I'm not sure what the resolution to that ever was. I've not tried to access that data myself. That's definitely a terrestrial origin signal. I'm trying to think if there's any other fun things. So LIGO can see, we talk about seismic waves and earthquakes. If you think about all the shores of the ocean, the waves lapping on the ocean shore, it turns out that there's a kind of natural period for this. It's about once every 6 seconds, so 1/6 of a hertz. It's called the microseismic peak, and the detectors pick up the noise at that frequency, even though they're hundreds of miles away from the ocean. They can measure the waves lapping on the shores of the continents, if you like, which I think is kind of a mind-boggling one. They're also sensitive enough to measure the gravitational field of clouds moving overhead. So if there's planes flying by, then quite often we veto the data because the metal will attract the mirrors as well. But clouds have mass, and thankfully they move very slowly, so they're easy to just control away from the system. But nonetheless, you have to do that. And of course, there's the effect of the moon, the biggest tide of them all. So over the course of the month, the arms are naturally stretched and squashed by the tidal field of the moon. So that's all easy to correct for because you know exactly what you're looking for in that case. Dispersion? Is that a question about the gravitational waves or?
Yes. Do
Yeah,
they exhibit gravitational waves exhibit dispersion?
This is a good question. So because of the effect I was saying that they're really weakly coupled to matter, they don't really disperse at all as they're moving from the source, which is a really good thing because it means that you can look directly into the heart of like a supernova. If the motion of the matter in the supernovas rapid enough, then we would be able to see what was going on directly in the middle without all the intervening layers being in the way.
So even dark matter won't do it.
No, it's I mean, the only thing that can really disperse gravitational waves is what I would call like gravitational matter, by which I mean black holes, basically. Neutron stars can do it, but they're very small. So if the wavelength of your gravitational wave is thousands of kilometers and a neutron star is only a 10 or 20 kilometers across, then it doesn't have much of an effect, and they're sufficiently, uncommon that there's not really much of an effect. You do get weak lensing, so things like galaxy clusters, the gravitational waves will be distorted in the same way that light waves are. But it's not, I wouldn't classify that as dispersion so much as just lensing.
Ending, yeah.
I think our last question tonight is the one from Ted. Thank you. And he's asking about the change in frequency on the clip that you played, John. Was that due to the source or material in the very long path?
So the frequency of the wave is twice the orbital frequency of the star. So that's why you want neutron stars and black holes, because it's only those that are small enough that they can actually orbit hundreds of times a second. So as they're orbiting, the radiation is carrying away energy from the orbit, and that makes the orbit shrink. And because it's obeying Kepler's law, the period will shrink as well. So the frequency of the wave will increase, and it's like a runaway reaction. So as the inspiral goes on, they get closer together, and the gravitational wave gets stronger and it gets higher in frequency all at the same time. So the amount of energy it's carrying off gets greater. And so they come together in this final collision.
Thank you, John.
Do you get interference patterns? You do. The ones that we've seen so far, we've not seen any evidence of interference. It is something that people look for, but they're sufficiently separated in time that there is not really an issue with interference anyway. For LISA, this is much more of a concern, because there you will be measuring long duration signals more, and they will overlap and interfere with each other.
Thank you.
Yeah, I see where your questions are coming from now. I'm thinking about it. They do behave an awful lot like radio waves, I have to say, except for the dispersion thing. There's some fun papers from some of these relativists in the 60s and 70s who started playing around with black holes, like Kip Thorne and people like that, looking into what kind of analogs you could do between gravity and electricity. I think for this audience, I will finish by saying that you can produce what's the gravitational analog of a coaxial cable, is one of the things they investigated. So you could actually produce this, but it would have to have an almost infinite density. And instead of having an inner wire and an outer jacket, you only need the inner wire, as it turns out. So if you go away and want to do some further reading, I would highly recommend looking up that idea. I think that's a fun place to end. That's well beyond the realms of us ever producing such a thing, unfortunately.
Yeah. Thank you so much, John. We'll get you back in a year or two to update us with new developments in the field. That was fantastic. And
there's a lot more astrophysics stuff that I can say, and I would love to come back and talk to you again.
Yeah. Thank you so much. One thing I love about your department, and I visited every time I was there, I think, and that is the photograph of Einstein with the staff in the early 20th century on the staircase. I think it's great.
Yeah, I wish I had been around in those days, but then again, I would have lived to see LIGO if that were the case.
Yes. A round of applause and standing ovation and stamping of feet and all that kind of stuff. Fantastic. Really good. I'd like to just conclude this evening by allowing Callum some time to share observations as well. Callum, you can share your screen if you wish.
Great, thanks, Paul. I'll certainly try. Where's it gone? That's the one, I think. Okay, is that showing up okay for everyone?
Yes, that's working.
Excellent. So this is just a quick update on my magnetometer, which was out of commission for quite a long time whilst we moved house. So I just thought I'd just a couple of interesting little learnings maybe that might catch out the unwary. Anyway, this was my basic design. I went over this on a previous talk, just using a flux gate magnetometer, counting the frequency and measuring the frequency, and using a temperature sensor to correct for the violent changes in frequency that the sensor does to temperature. So, and using a Pi0 Wi-Fi connected data logger, basically. So I went into that all before, so I'm not going to talk too much about that. But having moved to, and that was just the parts from the previous one, using the Pi Pico and the Raspberry Pico and the Pi0 as the counting components. But having moved from rural Gloucestershire to rural Orkney, I discovered that I'd have to place my magnetometer head somewhere a little quieter, and there wasn't any power or Wi-Fi or anything out in the spot where I wanted to choose it, which is on this lower left picture, where the blue arrow is pointing, is where I decided I want to put the magnetometer head. There are power lines coming across to the house, and there's also a wind turbine, which you can't see there, but just to add some extra electromagnetic noise around the environment. But that was where I wanted to decided to put it. So I decided to update my hardware. This was in test mode, so the actual wiring isn't quite as bad as that when it went into the deployment, but not far off. I know all of you electronic engineers will be turning in your graves, but it works well enough. So rather than using the Wi-Fi Pi0, I decided I'd have to use I'd use power over Ethernet and just put a single Ethernet cable out to where the station would be. But the Pi0s that I had didn't have any Ethernet ports, of course. I thought about replacing it with a Pi4, but of course there's no Raspberry Pis available due to the worldwide shortages. So I went around my junk box and found a Raspberry Pi 2B, which nicely has an Ethernet port and a few USB ports, and used a 12-volt PoE splitter to power up the Pi and the rest of the electronics. And I had all the electronics previously in this small box, and it all just fitted after having put the Pi 2 in, which was the biggest struggle of the project, was getting it all into the same box. I suppose I could have got a new box, but being mean and miserly, I decided just to try and keep it all in the same box. I didn't really want to rewire up the plugs and stuff. So this was my new magnetometer head. The old one was just in a big plastic box, which I buried in the garden just a foot or so down. For the new one, this is actually kind of like the Aurora Watch recommended magnetometer head. So you get a big bit of a length of plastic drain piping, and you put it down at the bottom of that and fill it up with insulated fiber, and I had lots of bubble wrap left over from having moved house, so I filled the rest of it up with bubble wrap and then buried it in the ground. Burying it in the ground was actually the hardest part of the job, because after about a spade's depth you get into big rocks and rubble and stuff. So it was hard work. I spent maybe a couple of days just digging the hole, not continually, but spending an hour or two a day, a couple of hours each day just to get the hole deep enough to leave a bit of it over above the ground. I also built myself a little shed for the electronics to sit in, little rabbit hutch. You can see on this picture on the left, the method in Orkney for stabilizing structures is to fill them full of rocks. So there's a shelf full of rocks there to stop it blowing over in the wind. And on the right, there's another set of rocks on top of it to stop it blowing over in the wind. So this was when I first got it going. I found that the signal was quite noisy. I'd actually started off just using a 5-volt PoE splitter, empowering it from the analog circuitry and the Raspberry Pi from the same supply, and that was obviously a bad decision. I also updated the code so that it would generate the graphs automatically every 5 minutes. So these huge spikes are when the processor's doing the plot generation. So obviously that's a quite undesirable effect. So I shifted away from the 5-volt to the 12-volt and went back to my old 12-volt power supply that I'd built for the previous incarnation of the design. This was just after I'd switched off the automatic generation of the plots, and so still had very noisy signal, which was pretty undesirable, really. And all these spikes you can see are the times when I've manually generated the plots or done the nightly one. So having cleaned it up a bit and got it buried in the ground, this is this sort of plots I've been getting. So this is a fairly quiet day showing the diurnal change, and the temperature does vary by a few tenths of a degree. At that depth, I think I might bury the head a bit more in some more soil and put a plastic bucket up and mound a bit more earth over the top of it just to try and dampen that down a little bit, but it's not too bad. The temperature signal has quite a bit of jitter in it, and that's just because of the resolution of the temperature of the sensor, the temperature sensor, I think. So that's why it looks broader at some points and thinner at others. This was the plots just from a few days ago, March the 23rd, which we had a splendid display of the Northern Lights up here. So it started off in the early evening and then went fairly bananas around about midnight and then into the early hours as well. Just a couple of my pictures of the aurora that night from up here, which were quite splendid. And yeah, you can see my power lines on the bottom right there of the picture. Unfortunately, all of the electrics are overhead in Orkney, but it's just something I have to grin and bear with, really. Right, so that was it really. I just a very quick update. It's all operational now, so I'll be sending off my reports to John and Paul at the end of the month again, and hopefully that will have another interesting set of results to go with all the rest of the magnetometry results. And I'm also thinking about my next radio astronomy project. So the house had an old satellite dish that was used for internet broadband, which I've not using anymore. So I've got an old satellite dish which I might be able to use for something, though I'm thinking more along the lines of doing something on VLF, but I've not quite decided how to do that yet. So yeah, all good fun.
Thanks, Callum. We wait with bated breath. That's some very nice mag data you got there, and some wonderful photographs. We're very envious.
Yeah, it's a lovely part of the world. So, and if anyone's ever up in Orkney and visiting, then do give me a shout, and we'll grab a cup of coffee or something somewhere, or you can drop down.
I think there might be a chat. I can't.
Yeah,
Don's talking about eliminating the 50 hertz.
Yeah, I don't think I get any, I'm not getting 50 hertz in my signals.
How long's your Ethernet cable?
How long is it? That's a good
Yeah.
question. It's armored Cat6, and it's from the nearest house to the point, and that's probably about 10, 20, 30 meters, maybe 40 meters. 10, 20, 30, 30 or 40 meters, I think. But then I also have some just another 10 meters, which goes to the PoE injector, the PoE router. Sorry, so I've got a 4-port PoE router in the where in the house for feeding any external things. So I'm planning on putting up a Meteor camera at some point. Yeah. I haven't had any problems with the PoE and dampness so far. All of the electronics are in a sealed plastic box inside the shed, which has got the PoE splitter. Where I've got a little external box which is not quite filled with sealant yet, but it will be filled with certainly with sealant to try and stop anything getting into that part.
Yeah, it can be a challenge.
Yeah, so yeah, there are sealing things need to do. We do get quite a lot of driving rain.
Well, thanks for sharing that, Callum. Thanks for sharing that. Excellent.
And if anyone wants any code or anything, just drop me an email. So my email address is there. So yeah, if anyone's wanting any code or ideas or other design things, just let me know.
Thank you. Thank you very much. Next month, in fact, it's May, in fact, the very beginning of May, we've got another academic from Glasgow University, and it's an evening all about the Fireball Alliance and an update on the meteor observation, the UK meteor beacon and observations. So see you all again next month. Take care now. Good night.
Thank you, everybody.